And now comes the reason why this is being discussed at all, which is the orthogonality theorem. I don't want to just reproduce. I mean, it's extremely well done, and I'm impressed. But I'm supposed to give you some intuition about this stuff. So here are a few kind of tricks we have learned so far that you might not have noticed that we have learned. But so one thing we have learned that you say we are working with complex numbers, so I can take any complex matrix and do a measurement. But if I take any complex matrix, any M of finite square matrix, I can always write it as a Hermitian matrix H1. Let's call it RE for real plus I. And this is, literally what we already know, because we know that for every entry, we can write X plus I, IY. And, it's a bunch of entries. I can put indices on it, if it makes you happy. So that's all that the statement is. But this statement says, if I know how to do things with Hermitian matrices, I'm fine, because other matrices can be expressed in terms of that. So that was one trick we learned. It suffices to know real numbers. In other words, in this language, it's called Hermitian. Correctly pronounced, it's Hermite. It's one of these wonderful French mathematicians. Next trick wasn't trick, but it was calculation. And it's not true for any set of matrices. They have to be a group. And what we used about the group are two important things, is that group elements have an inverse. And multiplication of a set of group elements returns the same set. That's called rearrangement theorem. So we use those two things to prove something that, again, I didn't find very obvious, that if I have a group element and I want to write a matrix representation of the group element, that matrix representation can always be brought to the form that it's Hermitian conjugate, which also means that Hermitian conjugate of G is same as the matrix of the inverse element. And remember, every group element has its inverse. So I can write it upstairs or I can write it in here, but basically Hermitian conjugation for unitary matrices is same as finding an inverse matrix. So that was trick number 2. Trick number 3, which is very, very important, is, what are we doing? We are trying to get answers from theories described by symmetries. So, if I'm trying to measure a kilogram of something, it should not matter what lab I do it in. It should always give me a kilogram. So there is translation rotational symmetry that connects different laboratories, and the answer should be invariant. So then you might ask yourself, how do you construct invariant things given a symmetry group? So here is one way to do it. It's called averaging. So if you have some matrix and one of these guys, which is a matrix of finite dimension, And if I bang it by the representation and I sum over all elements of a group, and I divide by the number of elements of the group. What that operation means is I take my object and I rotate it all possible ways. And then I find what's the mean weight of, my pizza piece by averaging over it. So this is a group average. And this gives me a matrix, let's call it M suggestively. And this matrix is invariant because if I multiply it by any group element, let's say, call it H, times this matrix, what it does is on the right-hand side, I just get product of two group elements, average over all group elements by rearrangement theorem. This is the same sum. So this quantity is now not one number like a kilogram, it's n square numbers modulo the fact that matrix is Hermitian, etc. So it's actually a smaller number, but basic thing is that these are all invariant numbers. So this is one cheap way of using invariance, and that's what we did in proving the previous theorem. We're constantly averaging over the group to make sure that the answer doesn't depend on which way my original matrix was defined in the group. So these are kind of the tricks we did. And now what character orthogonality theorem will say, there are group elements, there are H of them. I use notation order of the group. Then I say there are different representations, and there is a special set which I'll give special names called irreducible. So there is, E-rep name. And then I say, should be IJ. So this all looks pretty complicated. But what we are really doing is we're saying, when I have H group elements, I can put these guys into little vectors where all this stuff corresponding to the first element, second group element, and last group element. It's called the block matrix or vector. It's a vector which has order of the group, but when you look at every box separately, it's actually something that has a bunch of other labels. It's called quark, it's red, and it has spin 3 or whatever. But it's a vector if you squint and only look at the blocks. So this is a vector. I can look at the magnitude of this vector by taking complex conjugates of it. So I take this whole thing, turn it sideways, and that's what we are actually doing. That's what this formula here means. I take the vector and I multiply it by its complex conjugate. And now what do I expect? Expect the magnitude of this vector, and I have chosen the axis very cleverly. I will find out that axes are orthogonal. That's why it's called orthogonality theorem. And if I'm using the same subspace, so alpha beta belong to same era, and if I have aligned indices in the correct way, I'll get a non-zero answer. And that's true of good orthogonal bases. And these irreducible representations are a magical choice of representation such that this is orthogonality. So that's what we are trying to prove next.